Imagine you are sealed inside a steel structure roughly the length of 3 football fields, moving at speed through open ocean, completely out of sight of land, carrying more than 5,000 human beings who have no access to the internet, no ability to call home freely, no bank branch, no grocery store, no emergency room outside the one built into the hull, no external power grid, and no option to stop and restock when something runs low. Now imagine that every single one of those 5,000 people needs to breathe, and that the air they are breathing is not the unmanaged atmosphere you walked through this morning. It is engineered. Every cubic meter of it is monitored, filtered, circulated, chemically analyzed, mechanically regulated, and conditionally treated before it reaches human lungs. The question you should be asking is not how an aircraft carrier fights. The question is how it breathes, because if it stops breathing correctly, nothing else it does matters at all. The first thing most people never think about when they picture an aircraft carrier is volume. Not the volume of weapons, not the volume of aircraft, the volume of enclosed, inhabited space. A Nimitz-class or Gerald R. Ford-class carrier contains somewhere in the range of 6 million cubic feet of internal habitable volume. It is not a ship in the way most people conceptualize ships. It is a building that happens to float, and buildings of that scale, filled with that density of human occupation, generate environmental conditions that would be catastrophic if left unmanaged. Each person exhales roughly 200 cubic centimeters of carbon dioxide with every breath. Across 5,000 people over 24 hours, the accumulated respiratory output of the crew alone would render the internal atmosphere lethally toxic inside hours if the ventilation architecture were not continuously removing and replacing that air with engineered precision. This is the first constraint the ship cannot ignore. Air is not a resource you restock from outside. It is a resource you must perpetually manufacture from conditions that are themselves constantly shifting based on where the ship is, what the crew is doing, how many jet engines are running on the flight deck above, and whether any compartment below has been sealed for security or damage control. The ventilation system aboard a carrier of this class is not a single system. That framing is the first place civilian logic breaks down. It is a network of interlocking subsystems, each responsible for a discrete zone of the ship, each operating under its own pressure parameters, each capable of being isolated from the whole without collapsing the whole. There are hundreds of fans distributed across the vessel, ranging from massive axial units moving thousands of cubic feet per minute through primary passageways down to smaller recirculation units serving individual compartments. The ductwork, if laid end to end, would stretch for miles. The system is deliberately segmented because a carrier must be able to sustain a catastrophic event in one section and continue functioning in all others. If a fire breaks out in a lower machinery space, the ventilation serving that compartment must be shut down immediately to prevent the system from acting as a bellows, feeding oxygen to a fire that could spread through the hull. The same duct network that keeps people alive in normal operation becomes a liability in emergency conditions, which means the system must know at all times exactly what is happening in every zone it touches. This is where the system becomes something more than mechanical. It becomes a sensing organism. Distributed throughout the ship are gas detectors calibrated to register deviations in atmospheric composition at levels well below what a human nose could detect. Carbon dioxide accumulation is monitored continuously because it rises subtly and dangerously in spaces with restricted airflow and high occupancy, particularly in berthing areas where several hundred sailors sleep in racks stacked 3 high in rooms designed for efficiency rather than comfort. Carbon monoxide is an equally persistent threat in a vessel where jet propulsion systems, generators, and vehicle engines operate simultaneously, and where exhaust pathways are engineered with great care, but never with absolute certainty. If you were sleeping in a lower berthing compartment during a prolonged high-tempo flight operation with the flight deck above cycling aircraft engines at sustained intervals, the air flowing through your compartment has already passed through a filtration and conditioning sequence designed specifically to intercept the combustion byproducts that would otherwise migrate downward through hull penetrations and poorly sealed structural gaps. You are breathing air that has been actively defended on your behalf, and you likely have no awareness of it. Here's what most people never consider about the geometry of this problem. A carrier does not operate in a single climate. It operates across the full range of Earth's maritime environments, sometimes within the span of a single deployment. A carrier moving from the North Atlantic into the Persian Gulf passes through zones of dramatically varying temperature, humidity, pressure, and particulate content. In the cold North Atlantic, the challenge is thermal management of interior spaces and preventing condensation from forming in critical electrical compartments. In the Persian Gulf, where surface temperatures can reach conditions that stress metal and human physiology simultaneously, the challenge reverses entirely. The air conditioning load required to maintain habitable internal temperatures while the ship is surrounded by an ambient thermal environment in excess of 40 degrees Celsius is staggering, and it cannot be borrowed from outside. The carrier generates its own cold. It generates its own heat. It manages its own atmospheric pressure differentials between areas of the ship that are below the waterline, at the waterline, and above it, all of which interact with external conditions in different ways. The system must adapt continuously, and when it fails to adapt quickly enough, the consequences begin with discomfort and escalate towards something more serious than that. Humidity is where the human body begins to register the failure of atmospheric management before any instrument alerts the crew. In the tropics, without aggressive dehumidification, the internal spaces of a ship this size would accumulate moisture at a rate that would begin degrading electronics within days, promote mold growth in soft materials within weeks, and create a physiological burden on every person living and working inside the hull. The human body regulates its own temperature through perspiration, and perspiration works only when the surrounding air is capable of absorbing moisture. In a saturated atmosphere, that mechanism collapses, and the thermal stress on crew members performing physical labor in confined machinery spaces becomes medically significant. The carrier runs large-scale dehumidification systems in parallel with its cooling systems, and both are powered by the same nuclear plants that propel the ship, which creates an integrated dependency chain that has no external backup. If the nuclear plant reduces output, every system on the ship must shed load in a negotiated sequence, and atmospheric management competes directly with propulsion, communications, weapons systems, and medical equipment for the power that remains. The prioritization of that load-shedding sequence is one of the most consequential engineering decisions embedded in the ship's design, and it is made by systems, not by individual crew members reacting in the moment. But this creates a new vulnerability that the ship's designers understood from the very beginning. The air that is being managed is not only the air inside habitable spaces. It is the air inside every enclosed system on the ship that contains a human, a combustion process, or a sensitive electronic assembly. The aviation fuel system, running through multiple levels of the hull, exists in compartments that require careful atmospheric control to prevent the accumulation of vapor concentrations that could reach explosive thresholds. Aviation fuel releases hydrocarbon vapors at a rate that varies with temperature, and aboard a carrier, aviation fuel is stored in enormous quantities and moved continuously through piping systems that are always under some level of mechanical stress from the ship's movement through the ocean. The ventilation of aviation fuel spaces is deliberately separated from the main air handling system, uses explosion-proof mechanical components, and maintains forced negative pressure to ensure that vapors move outward toward controlled exhaust points rather than migrating into adjacent inhabited spaces. If that negative pressure fails during a period of active fueling operations, the exposure risk to the crew working in adjacent passageways is not theoretical. It is a specific, calculable, documented hazard that the system was built to eliminate, and its elimination requires continuous powered operation of dedicated fans that have no natural backup except the emergency electrical systems that the ship also generates internally. This is where the pressure intensifies. Everything on this ship that controls the atmosphere runs on electrical power. The ventilation fans, the gas sensors, the dehumidifiers, the air conditioning compressors, the fuel vapor exhaust systems, the medical oxygen generation equipment, the fire suppression controls tied into the ventilation network, all of it is electrical. And all of the electricity comes from reactors that are themselves housed in atmospheric environments that require careful management of temperature, humidity, and access-controlled air handling to maintain the safety parameters of nuclear operation. The reactor compartments have their own sealed ventilation loops that do not exchange air with the rest of the ship under normal conditions. They maintain their own pressure differentials. They are monitored with instruments that measure not only conventional atmospheric composition, but also radiation levels that would indicate a breach of containment before any other symptom appeared. If you were to map the airflow of the entire ship as a fluid dynamic diagram, the reactor compartments would appear as islands, isolated from the main circulatory system. Now we're managed by a parallel network that operates under its own logic and its own safety hierarchy. The people who work in those spaces live under a different atmospheric protocol than the rest of the crew, and the interface between their world and the rest of the ship is governed by systems designed to ensure that nothing crosses that boundary except the people authorized to cross it. 5,000 people is an abstraction until you start thinking about what they produce. Each person generates heat, moisture, carbon dioxide, and biological waste in quantities that are individually trivial and collectively enormous. The atmospheric management problem is inseparable from the thermal management problem, which is inseparable from the sanitation problem, which connects directly back to air quality through the ventilation of waste processing spaces, food preparation areas, and medical facilities. The ship's sickbay ventilates under negative pressure relative to surrounding passageways, exactly like a hospital isolation room, to prevent the airborne transmission of pathogens in an environment where 5,000 people cannot simply be sent home if they develop a respiratory illness. The kitchen exhaust systems handle the grease-laden air produced by feeding that population at continuous intervals across every hour of every day, routing it through filtration before it re-enters the general circulation. The laundry facilities, the workshops, the paint lockers, the battery rooms where hydrogen accumulates as a natural byproduct of charging cycles. Every one of these spaces has its own atmospheric management requirement, and every one of them connects back to the same integrated system that has no margin for a sustained failure. Now picture what happens when it begins to fail. Not catastrophically. Not in a way that triggers alarms and emergency responses, but in the subtle, cumulative way that complex systems often fail first. A sensor in a berthing compartment begins reading slightly low on airflow because a duct damper has partially seized in a near-closed position. The crew in that compartment begins experiencing elevated carbon dioxide levels during the overnight hours when they are least likely to notice anything other than a vague sense of fatigue and difficulty concentrating in an environment where cognitive performance is already being pressed by irregular sleep schedules, high-tempo operations, and the psychological weight of extended isolation at sea. A 2 or 3% elevation in ambient carbon dioxide is not a crisis that announces itself. It is a background condition that erodes the margin of human performance at exactly the moments when that margin is most needed. The maintenance technician responsible for that section of ductwork is simultaneously responsible for 40 other points of inspection across a ventilation network that spans multiple decks and hundreds of thousands of square feet. The system is monitored, but monitoring is only as reliable as the calibration of the instruments and the availability of the personnel to respond to what those instruments report. The carrier does not have the luxury of calling a contractor. It has the people who are already there, working within a logistical reality that has no external supplement. What makes this system genuinely remarkable is not any single component. It is the design philosophy embedded in the way the components relate to each other. The ship is designed to sustain damage and continue operating, which means the atmospheric management system is designed to sustain partial failure and continue providing baseline life support. Redundancy is built into fan systems, control pathways, power feeds, and sensor networks in a way that reflects a fundamental engineering conviction. No single point of failure should be permitted to propagate into a life-threatening atmospheric event. The ship can lose individual fans and redistribute airflow. It can lose a sensor cluster and rely on portable monitoring equipment carried by damage control teams. It can isolate an entire zone of the ship and maintain life support in all other zones while that zone is addressed. What it cannot do is lose the nuclear power plants that drive all of it, which is why those plants are protected by a depth of redundancy and a culture of maintenance rigor that has no equivalent in civilian infrastructure. The atmospheric management of the ship and the nuclear management of the ship are not separate problems. They are the same problem viewed from different angles, because both ultimately answer the same question: how do you keep 5,000 people alive when the world outside the hull cannot help you do it? The philosophical architecture underneath all of this is one of design self-sufficiency that goes well beyond what any civilian facility has ever been required to achieve. A city on land can always, in the last resort, open a window. It can call for outside air, outside power, outside expertise, outside supply. The carrier has no window to open. It is sealed into its own logic, its own resource envelope, its own atmospheric reality, and it has been designed from the hull up to treat that isolation not as a vulnerability, but as a baseline condition that every system must be capable of surviving indefinitely. The air inside this ship is not borrowed from the ocean around it. It is manufactured, managed, and maintained by systems that themselves exist within the air they are managing, creating a closed loop of engineered interdependence that has been tested over decades and refined through every deployment where something did not work exactly as intended. And there is one more system inside this loop, one more atmospheric problem the ship carries with it, that most people who study carriers never examine closely. It involves the spaces where human judgment under extended atmospheric stress produces outcomes that the ventilation system alone cannot correct. That is where the next layer of this engineering problem begins, and it remains, in many ways, the one the ship has never fully solved.